So this is Catherine de Medici. She was the Queen of France in the 16th century. She married Henry II, I think. I'm going to make a note. And she ruled for about 12 years while her son was too young to rule. So she was the regent queen of France. There was also, the wedding was approved of by Pope Clement VII, who was also her cousin. So same family. And, well, I can't swipe. Okay, there we go. And then we also have the patriarch of this whole family, Giovanni Debits de Medici, and he is the one who basically set this family on the path to having two regent queens of France, two popes, archdukes and dukes all over Europe. And how did he do that? Well, he was a banker, and there was a lot of luck involved, a lot of right time, right place kind of things. But he created the richest family in Europe in no small part due to a single abstraction, a very powerful abstraction. That abstraction was double entry bookkeeping. This thing, it has been around since at least as far back as the 14th century, maybe further. He didn't invent it. It was not the Medicis that invented it, but they used it, they refined it, and they perfected it. And it's still being used today. It's what you have to learn as a CPA. Now, I'm going to explain double entry bookkeeping, but I'm not an accountant. I'm an engineer. So it's all from that perspective. This won't get you to pass the CPA exam. All right, so the basic things about it are there are accounts and transactions. These are the two basic concepts. Accounts have a column for debits and a column for credits. And that's just an amount. Each credit and debit is an amount. And transactions have the amount of the transaction and the credit account and the debit account. Okay? And then you combine all these accounts together, and you call that a book, because that's where they recorded it. Also called a ledger, if you're into that. One of the reasons why this abstraction was so powerful was because it had mathematical properties that you could talk about. It had laws, you could even say. So if it has laws, then you could call it like a theory. It's a theory of accounting, double entry bookkeeping is. And it's well defined, it's precise, it doesn't have corner cases, it tells you what to do in every possible case if money is transferring from one account to another. And then it also says how things compose into a book, how the accounts compose into a book. So it's a composable abstraction. This is one of the laws. It says that all the debits in the book, if you add them up, and all the credits in the book, you add them up, and the two sums should be equal. Here's another thing. If you have different types of accounts, and you know, you keep track of, you know, your debts and how much money is coming in and what people are investing in your company. Well, you have different types of accounts, and here's just a relation. This is how they are related when you add them up. And here's another thing. I've kind of turned this more into like a mathematics thing. If you take a book and add a transaction to that book, and then you add another transaction here, that should be the same as adding the second transaction, the TR2, first, and then adding. I mean, that's basically saying the order of transactions doesn't matter, but in a very precise mathematical way. And it's that kind of precision that made this thing so powerful. A lot of people talk about the double entry bookkeeping lets you detect certain types of errors, and that's important, but I don't think that that would have propelled the Medicis to take over Europe. What it really is that they've found some really great abstraction that captures something that other abstractions didn't, other theories of accounting didn't. Okay, here's a tweet. So I'm going to have a few of these tweets throughout the talk, and if you are so inspired, you could tweet them out. Instead of me just saying it and you have to write it down, here we go. This is what I want you to tweet. We talk a lot about abstraction, but something is only abstract relative to something more concrete. So you'll hear people say, oh, I made an abstraction, but then what are you abstracting? You haven't even, you can't even tell me, you know? Oh, a class, it's an abstraction. Of what? What are you abstracting? So let's do that exercise after that little rant on this double entry bookkeeping. What is it representing in the real world? So the answer is gold, right? I mean, if you were going to like get rid of all the abstractions all the way down, it's gold, money, right? It's not, you know, gold is kind of like the primordial money. And it's not just gold, like, so you have an account, so that's kind of like a safe. That's like where you put your gold to keep it away from the other gold. So, you know, this is this person's account, this is this person's account, this person's safe, this person's safe. And so what is a transaction? Well, a transaction is movement of gold from one account to another. Okay? And then what is the book? It's the whole history of all the motion between accounts. Okay, so we've reverse engineered this abstract system down to its physical, you know, concretion. But what we do as engineers is go the other way. We take something physical, or at least somewhat not abstract, and we try to abstract it so that we can, you know, build information systems about it. So that's what we do as engineers. And my name is Eric Normand. This talk is called Building Composable Abstractions. I'm kind of on a mission to develop a process to build composable abstractions. We don't talk enough about how this process works. There's processes for dealing with existing abstractions and refactoring them into something else. But there isn't enough talk about how to create the abstraction in the first place. So today, this is an evolving process, and this is the current iteration of that process. So let's get started on that. Everybody has probably heard this bit of advice. Don't just start writing code. Like when you're starting to work on a piece of software, don't just start writing the code, think about it first. Okay, that's kind of like a pseudo process. Like let's try to write it out in like step by step. Okay, so first we're going to take an assignment, then we're going to think about it, and then we're going to implement it. That sounds good, except for that number 2 part, which is indistinguishable from procrastination. Because thinking, you're not actually producing anything. And what are you supposed to be thinking about? And how are you supposed to think? those are the kinds of things that, you know, an experienced programmer can tell you to do, and they obviously have some way to think, but you can't just translate that into instructions to think about it. So it's unfortunate, but this is kind of how I feel the state of our industry is right now with this process. And, well, I hope to do better today. So what are the objectives for this process? I want it to be able to consistently produce good abstractions. And I'll talk about what good means for an abstraction. I want anyone to be able to do it. And that kind of means you don't need like a PhD to do it. You should be able to use the tools that you already know to do it. Now, of course, if you know more tools, if you have a PhD, you might do it better, right? You might come up with a better abstraction. That's always possible. Like, you know more, you have more tools available, you can do more. And then I would like to make sure that we can do it as a team. We work in teams now when we're building code. So we need to be able to talk about it, discuss it, and build this thing as a group. The abstract says I'm teaching Denotational Design, which is a process developed by Connell Elliott. And this talk was, or this current iteration of the process was largely inspired by this process, by his talks and his papers and stuff on his blog. You should read it, it's really great stuff. But I don't want to call what I'm doing denotational design because he has a specific meaning behind that, and I'm probably deviating from it as I adapt it to my objectives. So I apologize if what you wanted was something like exactly denotational design. This is my own thing, but largely inspired by him. Go read his stuff. All right, so here are the real steps. So number one, physical metaphor. I love physical metaphors, and we'll talk a lot about that. Meaning construction. So before you get into the implementation, just like your uncle programmer said, you want to think about it. You want to build the meaning of it before you actually implement it. And then finally, you implement it. These things are roughly equivalent to a process that's called what's it called? Something about falling water, waterfall. Okay, so requirements gathering, specification, and then implementation. Okay. So just so you see how it relates. Whoa. Okay. So one, physical metaphor. When we do anything in the world, when we think about anything, it's often, if we do some meta thinking and think about how we're thinking about it, most things are actually physical metaphors. Okay? So we want to take this thing that we need to abstract and really find the physical metaphor for it. Physical metaphors, the choice is important. So let's go through. So we noticed that in the accounting example, we didn't just count money. Like, a naive accounting system might be like, well, just write down how much money is in each account, and that's accounting, right? And that's probably how a lot of people do their finances at home, right? Is they just keep track of how much money they have. But what's really powerful about the abstraction is that you're tracking the movement of money from one account to another. Because the money itself, like if you were piling up gold, it maintains its own count, its own amount, quantity. You can always count it later. Like you don't need, but what's lost is the motion. If you take some coins from this pile and put them into that pile, how much did I take? I don't know. Like I forgot how much I moved from one to the other. You've lost that. And what double entry bookkeeping did, and the reason it was so powerful, was it turned something that was lost into a trail of information. So we have a true information system. And so I just wanted to highlight that choice of physical metaphor is so important. Because if you were going to choose a different metaphor, you would come up with a totally different abstraction. And that abstraction might not get you to take over Europe and become the Pope. Okay, so there are different metaphors. And like you can't say that like one is right and the other ones are wrong, right? But you can talk about a good one. So let's just read this tweet. Good metaphors contain answers to important questions. Different metaphors might have different answers to the same question. So this is the kind of like maybe relativism of science, that there are different models and they're both good models, but they have different answers. So, you have a model like Galilean gravity, Galilean motion is different from Newtonian motion. They're both good, especially, on the Earth. Newtonian and Galilean often correspond very closely. But they're giving you different, they have different abstractions to them. For instance, in Galilean gravity, it's always down. There is a down. There's no down in Newtonian. So this is a tweetable moment. So we've been learning about space and movement since we were born. I mean, it's like you come out and you start moving, and eventually you start to gain some control over how you move. And so it's something that's like deep inside us to the point where it becomes intuitive. And our language is full of it, full of spatial metaphors. If you really start like digging into the words that people use, they're spatial metaphors. Like if I give someone an idea, I'm giving them an idea. Like that's talking about like taking it from my possession and putting it into their possession, right? It's physical, it's spatial. Okay. And we've been doing it so long, like it's so easy for us to reason about. That's why physical metaphors are so important. All right, another thing about physical metaphors, because we've been doing it so long and we live in the same three-dimensional space, we have common ground here, right? A good metaphor gives you common ground for discussion. This is the collaboration I was talking about before. You might disagree, but at least you're disagreeing about the same thing. So you might say, well, this person thinks that, the debits should go on the left and the credits should go on the right. I think the credits should go on the left and well, yeah, okay, you disagree. But like, you're still talking about, you have common ground for disagreement, right? All right. So I'm asserting right now that every problem worth solving has a good physical metaphor. Good meaning you can get common ground on it and you can intuitively reason about it. Okay? Everyone. That's what I'm saying. And this is the biggest point of contention, because I think that I've given this talk at a local meetup and talked to people about it, and the biggest objection is, well, yeah, your abstraction has that, but not mine. right? Mine is very abstract. It's like it has nothing to do with the real world, or something like that. Okay, so that's everyone that I've met, and I ask them what their abstraction is, I come up with a physical metaphor. I think they just give up. They don't even try, because I think they're thinking I'm talking about something else. So here's an example. I'll say, like everything has a physical metaphor, and someone will shout out, what about quantum physics? You can't reason about that. And then I'm like, well, you can. Like, it's waves and particles, and it might be unintuitive on a certain level, because you wouldn't expect the two-slit experiment. But then you do the two-slit experiment and you can reason about it, So you might need to gain a little bit of experience about how photons work. But once you do, like it totally becomes something you can reason about. So I've never met. Oh, is that a tweet? There it is. I've never met a good abstraction I couldn't turn into a good metaphor. Boom. Okay, so here's some possible metaphors that so accounting is all about physical gold moving around in vaults, right? But not really. Like, some of it's money, it's checks, it's it's like non-monetary stuff. Like, it's something so it's that's just the metaphor. It doesn't mean that that's actually what's happening, right? You walk into a bank, you don't see people. I mean, you might have used to, but now you don't see people walking around with bags of gold, put that into my vault, please, and you get a receipt. That would be cool, though. All right, so it's a metaphor. Doesn't mean it's what's really happening. So some cool metaphors. They should be really simple. Okay, and we're going to go over an example. Just want to reiterate, accounting is tracking the movement of gold from one vault to another. All right. Step 2, we're going to construct the meaning. In this step, you can't go to step 2 without step 1 done, because we're going to construct the meaning by mining that physical metaphor for answers to important questions. And this step is equivalent to specification. We saw that before. So you're trying to actually constrain the system to fit what you need it to do. You're specifying how it's supposed to work. There's a meaning, semantics, they're all kind of the same thing. My programming teachers all said stuff like this: focus first on the interface, not the implementation. Okay, that's what we're doing. Implementation is step 3. This interface, that's step 2. What does it mean to call this endpoint? What does it mean for this function to return this value? That's what we're talking about. We're talking about interface design. All right, so back to Connell Elliott's Denotational Design. He had some guiding principles. These are just things to keep in the background, and you keep them in the background because they guide you. Because design is always iterative. You don't plop down the perfect design the first time. You make something, you make it better, you throw it away, you make a new one, you keep iterating. Okay, so these are the 3 things. First one is adequacy. And then underneath I got written in software engineering terms. So can we express every use case? That's pretty clear that we want to be able to do that. Next, simplicity. I know there is actually a definition that this group holds to, but this is what he meant by it. It's clear and readable without unnecessary cruft. You don't want a lot of boilerplate. You don't want unnecessary constructs, stuff like that. No, simplicity, we tend to think of it as things being unentangled. And that's important too, but his definition is broader. But this is the definition that we'll use in this talk. And precision. Can we write tests? Okay, I mean, we don't always have to write them, but can we write them? Like, can we say this is what this is supposed to mean? All right, Connell Elliott will talk about how precision isn't really the goal. Precision is something that acts in tension with accuracy and simplicity, or sorry, adequacy and simplicity. Because it's so easy, if you're not being precise, to hand wave and act like it's simple or act like it's adequate. But until you sit down and write a mathematical meaning for it, you don't even know if you can do that, if you can be precise. And then often, once you are precise, it reveals, oh, this is not so simple after all. So this is a part of the process that still needs to be kind of really fleshed out. But what is important to preserve? There are these questions that we ask to mine our metaphor, because that metaphor has all that rich information. So we want to mine that and turn it into an abstraction. We want to dig down deep, and we'll get into that in a minute. So what's important to preserve? What things can we reject? Because as an abstraction is going to like highlight certain features of our metaphor and just ignore the rest. And then how are the important things related to each other? That's another important question. All right, so let's look at our example, which is bookkeeping. So what do we want to preserve? Well, one thing is transactions don't matter. The order of transactions doesn't matter. We want to preserve that. We don't want it to be a coincidence that transactions don't matter. We need to be able to get checks at different times. A check could come to this teller. That teller is faster, and so that two checks that arrive at the same time might then get out of order. That's okay. It shouldn't matter. At the end of the day, though, when we've processed all the transactions, we need to have the same answers. It doesn't matter what order they came in. Okay, persistence of amounts. You don't want gold to disappear. That's all that means. And movement between accounts. You want a kind of a history of the movement. What's not important? The color of the safes. Okay? Now, I say that, it's kind of like, duh, why would you? But like, when I say it, because of our metaphor, you can already just say, yeah, you're right. Right? Now, I gave this talk before, and someone it's like, oh yeah, but what if the red safes mean something different from the blue safes? Well, you don't care about the color, you care about the meaning, right? The red means this, that's what you need to preserve. Okay, so it's not the color, it's the meaning. And the color has no inherent meaning, so we don't need it. So where the safes are, doesn't matter. If I put this person's accounts over there, it doesn't matter. And then how the gold is arranged, or is it in bars or coins? And we're not concerned with that, and no banker really would be. Okay. All right, so then we take all those answers to the questions, and there are more than what we did. And we can just start to refine it and define it more clearly. So we're just increasing the precision, really. We have a book has a set of accounts, an account has a list of debits and a list of credits. A debit is an amount of money. So we're just elaborating all these things, and we'll take those equations that we had from the beginning, And one nice thing about using functional language is that we have Lambda Calculus. Lambda Calculus is math. Clojure is Lambda Calculus, or at least a subset of Clojure is Lambda Calculus. So we can just use Clojure to define these things. It's well defined. So let's look at it. We'll translate this. A book has a set of accounts into the meaning. Now, we're writing Clojure code, but we're still talking about meaning. We are not implementing it yet. It just so happens that Clojure is well enough defined, or at least the subset we're going to look at, it's well enough defined that we can use it instead of using a different mathematical notation. And you'll see, like book accounts, the function is not defined yet. We don't know what it does, but we can write a spec, right? That's another nice thing. We can write a spec. So we're going to say that the book accounts, we don't know how we're going to implement books. We don't know how we're going to implement accounts. Obviously, we won't use nil. We have this one function that takes the that returns the accounts for a particular book. We don't know how to implement this because we don't know what books look like, we don't know what accounts look like, but we do know that eventually our function will have these arguments and that return value. All right, now an account has a list of debits and a list of credits. This is another statement that we had before. Let's refine it more. So we'll have to define debits and credits. And there are many ways to define it, but just for this example, I'll just say it has to be an integer. They have to be integers. We don't know how account debits is defined, except we do know that it will return a collection of debits, and the account credits will return a collection of credits. Okay, so now we have this equation. So I'm just picking a few just as examples. Now we have the ability to, now again, it's still meaning, but we can define the meaning of book debits in terms of other things that are well defined. Mapcat is well defined, equals is well defined, reduce and plus and zero are well defined. Book accounts, we kind of promised to define it later, but we've at least given it a spec, so we're kind of safe in that sense. So we're just getting we're starting to relate these things together, and we can do that because everything is well defined. They have well defined meanings, and we can bottom out. That's kind of the term I'm thinking of. You have to bottom out somewhere. All meanings bottom out, probably in physical metaphor. Oh, meanings you define have to bottom out somewhere. Just like we bottomed out that debits and credits at integer. They're just integers, like an amount of cents. You could have a different thing that like represents a number of, like the number and a unit, right? But then that number would bottom out as an integer. And so you see, it's not clear. It's a process. It's an iterative process, but it is possible to define it and bottom out like that. Okay, so we haven't defined the meaning of everything yet. Just wanted to give you an idea of that. We're actually going to go through a complete example now. But another thing is, like, at some point you come up with a meaning, you have to revisit your metaphor. Just always remember adequate, simple, and precise. Oh, and one more thing about this. The cool thing is you're like 90% of the way to an implementation, right? That's really cool. Oh, and now we're at implementation. 90% there. Like, the meaning is runnable. If you choose the definition of your meaning properly, you can actually be almost done. Now, it doesn't mean it's efficient, it doesn't mean it's the best way to do it, or if it's even going to satisfy your system, right? Because this is all in memory. Like, we're not talking about like if you wanted to do it in a database. but it's the meaning of it. All right, so we're implementing this. Okay, so let's implement this. I mean, that's what everybody says, right? Just use a map. You're in Clojure, just use a map. You could use a map. It's fine. It's fine. But you could use a database. Like, that might be what you want to do. And so you would have to translate your functions that did, map cat into like a SQL query, right? Or you might have to you might want to do it all on the database, so in one big select statement. We've defined the meaning of it. Now you have to like constrain your implementation to the meaning. All right. So that was just a way to explain the process. Now let's actually go through the process and step by step develop a vector graphics system. Okay, just because we don't have a lot of time and the slides have limited size, we're just going to do squares and ellipses and two operations, rotate and translate. Okay, we're not going to do like scale and all that. No, you could, but we won't. We don't have time. I don't know why I can't do this. It's just slow. And then we're going to see Quill. You might think vector graphics, why not just use Quill? Well, that's a good question. And I want to show you, because Quill does do vector graphics, so I want to show you like why Quill is not enough, just to motivate what we're doing. Okay, so here's like the basic Quill draw function. And you can see the window is black. Okay, it just draws nothing, or just always black. If I want to draw a rectangle, I can say, well, put it at 100, 100, 200, 120, and then boom, it draws it. And it draws it white because I haven't set the color. So if I want to set it to red, I have to say fill. The fill color is red. And I have to do that before. So you can think the metaphor is kind of like, well, I'm going to dip my paintbrush in ink, and then whatever I paint after this, well, it'll be that color. Okay, so if we want to move that rectangle, we could change the 100, 100, but you can do this other thing called an Affine Transform, where you say translate 200, 100. And so it looks like, well, that just moves the rectangle over. So it's kind of like, from what I see here, I have a paintbrush. I'm going to move the paintbrush 100 or 200, 100, and then I'm going to draw my rectangle. But then that kind of doesn't work if I do a rotate. It's the other operation we want to do. So I've rotated a certain number of radians, and you see instead of just rotating the rectangle like this, it's rotated it around the origin. So that's kind of weird. So that's like saying, well, I'm gonna turn my body like this, and then I'm gonna translate 200, 100, and then I'm gonna draw my rectangle. Right? It's kind of weird. But then if we rotate after we translate, then it looks like that's what we wanted, where you just kind of rotated it there. So that's that's like saying, well, I'm gonna move over here, and then I'm gonna turn around my pen. So I'll have to go like that, and then I paint. Okay, and I don't know about you, but that's not how I paint. That's not how I think about shapes. So let's come up with a new physical metaphor. There are different possibilities, and we could explore all of these, and they're all actually pretty cool if you wanted to think about how to do this. And really, the possibilities are endless for different like vector graphics programs and the way they treat, the way they work, right? Like if you wanted to be a painter using a vector graphics program, you might think about how we did it, like dipping your paintbrush in. And if you wanted to do stencils or other stuff, it's a total possibility. But the one I'm going to use in the talk is shapes made out of construction paper. So you cut a shape, and then you can place it, right? So it's once you cut the shape out, you can't change the shape. You can put it down, you can move it around, you can rotate it. That's what I want to be able to do. And then I want to like be able to put one on top of the other, kind of overlap it. Okay, so then that's a good enough description to move on. I think we might have to revisit it and like clarify some things, but I think everyone's had that experience of cutting paper and then moving it around. Okay, so let's do this. I'm gonna do it in a way that is probably way more pedantic than you would do if you were to do this at home. But for this kind of thing, I think it's important to show your work, and so that's what I'm gonna do. I'm gonna show you like every little step. So first question, what's important to preserve? Let's answer that. We want to distinguish between shapes. We want to construct shapes, preserve them. You know, you can read. I don't need to tell you. Okay, let's go through some of these. So distinguish between shapes. Now I have to take this and make the meaning more precise. What do I mean by that? Well, what I mean is I have a cutout. That's the thing I've got. And then shape is like a property of a cutout. So that's that function shape of. It takes a cutout and it returns a shape. Okay? So that's my way of distinguishing between the shapes. Now, construct a shape. So if I wanted to construct a rectangle, I would give it a color and a width and a height. Now I put color, width, and height there because, you know, the paper that I'm cutting it out of, that has the color. So I can't really change the color, and it's, you know, it's prior to constructing the shape. Same with the width and the height. While I'm cutting it, that determines the size of the rectangle. All right, so then I just have some spec there. Same with the ellipse, it's the same thing. And it should return a cutout, not a shape. Okay, preservation of shape. So I guess what I mean is, if I move it around, it doesn't change from a rectangle to an ellipse, or the size doesn't change. So I can kind of spec that out. So translate, we don't know how it's defined yet. So I know it's going to take a cutout into numbers, and then it's going to return a cutout, and that returned cutout shape is going to be the same as the shape that I gave it. Same with rotate. Okay, so now I'm kind of saying, well, to be able to do that, I have to say that the shapes, you can check their equality. You know, there's a lot of stuff where you can check the equality, so I'm pretty good. It could be a number, could be a keyword, a string, you know, different stuff. Preservation of color. The same thing works with color. I don't want the color to change just because I'm moving it around. So I put that in there. I made an and. It's the same thing as shape of. Okay, now overlay order. So I want to be able to like say this green thing, this green rectangle goes on top of this red rectangle. You can go. It's like right here. Okay, so overlays, I can say, well, I'll construct an overlay out of two other cutouts, and that overlay is actually a cutout, right? I could say that. But now I have this dilemma, because I remember, a problem. I remember I said, well, every cutout has a shape and every cutout has a color, right? I don't want a corner case where some of them don't, like they return nil. That would be hard to deal with, especially while I'm still able to switch things around. So let me retry. It's iterative, showing every step. Let's say I made a new type called collage, and an overlay takes a collage and a cutout, and it adds the cutout on top of the collage. Okay, so now I can define a test check property where I say, well, given a collage and then two shapes, if I add shape A and then shape B, it's different from adding shape B and then shape A. Okay, that to me makes sense. All right, and now I had another point that was rotation and translation independence. So before we saw that if I translated first and then I rotated, it actually rotated it like around the origin still, and that's not what I wanted. So I want what I really want is I can translate it, I can rotate it, and then I can translate it again, rotate it again, and it's all like translation doesn't affect rotation and rotation doesn't affect translation. So I'll express that as another property, and I'll say that if I translate and then rotate, it's the same as rotating and then translating. That's a pretty good expression, right? Okay, so now I have this like test that I can run. Now rotation is additive. What I mean by that is if I rotate it, like I'm revisiting the physical metaphor, as you can see. So I take the thing and I rotate it so much, and then I rotate it again. It's the same as rotating that whole amount one time. Okay? Or if I rotate it 10 and then 20, it's the same as rotating 20 and then 10. Additive, I was imprecise, but now I'm being more precise. Translation, same thing. If I move it this way and then this way, I get the same result as if I move it this way and this way. Right? So I guess what I'm saying is I'm throwing away the history of the motion. I just want to know, where does it end up? Okay. So then also we need a draw. So finally, when we have this thing, we need to be able to draw it. And so when I got to this point and I said, you know what, I don't feel very satisfied with this. I've written all these checks, but I don't have anything. I'm not anywhere closer to implementing this. I mean, I've got empty functions that I could fill out. I started thinking, yeah, the reason is there's actually different ways to do it. You can define the properties, like let's take addition, right? I could say, well, I need something that's associative, commutative, it also has an identity that's 0, and I could just list all the properties and make those into tests. Like this is, that this operation is all conforming to these properties. Or I could say, I'll just use plus because it's already well defined. Then I'll construct the meaning instead of defining the meaning in terms of properties and constraints. Okay. So let's start over again. That's design. We have two types now. We have a cutout and we have a color. Cutout is actually a function. Okay. Now the reason I choose functions is because we're in Lambda Calculus. In Lambda Calculus, everything is a function, so you can always just use functions. They're Turing complete. You're never gonna go wrong with a function. And they also have some other properties that we can kind of lean on. Just like with plus, we can lean on associative instead of defining it or constraining it from the outside. So one of those properties is this function takes the tx, the ty, and the r, the translation and the rotation, as arguments. which means that every time you call it, you can pass in different arguments. Notice it doesn't take a shape. It doesn't take a color. It doesn't take a width or a height, right? So those things can't change. I'm defining by using the lambda in a certain way that those things can't change. And what things can change are the arguments. So I don't have to have all those properties anymore. I don't have to say, preservation of, I don't have to define a test check property that enforces preservation of shape. Okay, so I can throw away all that code. And then color, I'm just going to bottom out on a tuple of RGB. And I don't have anything interesting to say about color. Okay, finally, the other thing we can do is we can say, well, quill is we can bottom out to quill too. It's well defined. So why don't we just bottom out there? To do that, you kind of have to you have to understand quill well enough, but I think we do. Okay, so here's how you construct a rectangle. It takes a color, width, and a height, and it returns a function that is what we're calling a cutout that takes 3 arguments. And it just draws, it translates, rotates, sets the color, and draws a rectangle. We can do the same for ellipse. Boom. Now what does translation look like? Now we're getting somewhere. Translation is when you translate a cutout, it returns a new cutout, so a new function, and we're saying that you just add the tx's and you add the ty's and r passes through, and that's what you draw. So that's actually pretty cool because that's well defined. Everything in there, we know exactly how it works, and they don't have corner cases, so we can use it. Same for rotation. We're saying rotation is additive. Okay. Cool. Now overlay, and we're going to throw out that collage thing and just have two cutouts, return a new cutout, and we'll just pass through the tx, ty, and r to each of them, and that'll be our meaning. Remember, we're still in meaning. I have to remind myself too, because we're writing code, but it's well-defined code. Okay, and then draw, we can actually define that. We're just going to draw it with zeros, like, 0 rotation, 0 translation. Okay, so that means that we can define a rectangle, a red rectangle, a green ellipse, and then draw the overlay of the two. That looks good. So this is one of the nice things about using a well-defined language is that you can actually run it, right? Like you think about mathematicians back in the day coming up with abstractions. They actually had to do the calculations all by hand to see if they worked out. We can see if our abstraction matches our physical metaphor just by running it. It's awesome. Okay, but now here we have a problem. If I rotate that same overlay that I made in the last slide, we see that they separate. And that's not really what I had in mind. So I'm going to revisit the physical metaphor. Excuse me. If I put a green oval on a red rectangle, I really want to just reach down and rotate them. I don't want them to rotate independently and stop touching. I want them to be relatively the same, but on the whole table, I want them to be turned. Okay, so they don't move relative to each other, but they turn like that. And that's clearly not what's happening. I mean, there they're touching and there they're not. That's not right. And we know what's happening is they're both getting the R passed through, so they're rotating independently of each other. So, okay, so that meaning didn't really work out, so let's refine it or change it. Again, revisit. When I reach down, like I have a choice when I reach down to rotate those papers, especially if there's multiple things that I'm going to turn them. I can put my hand, boom, here, or I can put it here. I can kind of like grab one like this, or like take the corner of it. So there's really a choice of like, where's the center of rotation that I'm going to use here. Okay. So we can actually add that to the overlay function. So the CX and the CY, that defines the center point where I'm going to rotate around. And so now it's not so simple. We have to actually like do another affine transform. But basically what we're doing is we're going to say, because with an affine transform, when you rotate, you always rotate around the origin. So you have to move it to the origin, rotate it, and then move it back. So the origin, if I pick the center here, is going to be the negative, of the center. Move it back to the origin, rotate it, then add the center back in. Boom. Now you can do the stuff that was defined for that cutout. Okay, and so now we see that it does work. And if I pick the center, I can pick different centers, but if I pick the center right, I can get the whole thing to move around some point on the shape. That's cool. Right, and you see I'm doing taking the time and turning it into radians so that it's rotating in a nice way. Okay. The thing, we've seen it running. Like, why am I even talking about implementation? Well, you could leave it like that. You could. You could. But we've lost some stuff. Because we used functions, we're returning functions. Functions are totally opaque. You can't tell what is inside. So you can't ask it like, what are you? Are you a square? Are you a rectangle? What size are you? What color are you? We can't. It's all locked into that closure. We've also lost equality. We can't compare two functions to see if they are going to draw the same thing. And so because we lost equality, we've lost testability. We can't run properties on these things anymore. You could do some complicated thing using side effects, like render it to a canvas and then compare every pixel of the canvas to another canvas, but we'd have to work around this limitation. And then we can't serialize it, so we couldn't write it to a file or store it in a disk or something, store it in a database. At this point, if I had more time, I would take that lambda definition and the meaning definition, the semantics, and refactor it into a data-driven DSL. I would love to do that. And if you want to see that, I will gladly do it, like at lunch or during the break or something. Because it is a simple, step-by-step, no meaning change, purely syntactic transformation. And it's one of the reasons why I really like working with lambdas first. A lot of people jump to DSL first. But lambdas first, you can always translate it. Lambdas are Turing complete, so you're never going to go wrong. And then you can always translate it into like a little interpreter if you want. So that was the end of Act 2. Whew, let's take a break. Who knows who this is? It's Isaac Newton. Newton, obviously a big abstraction builder. He made Newtonian mechanics, optics, calculus. These are like really important really important abstractions, and he did them all with pen and paper. I mean, and you know, prisms and stuff. He had prisms. But this is like really amazing that this person was able to make all these cool abstractions in a time when that kind of idea was pretty rare. But the thing is, we as software engineers develop new abstractions every single day. I mean, some days you might just be fighting bugs the whole day. But very often we are developing a new abstraction every day. Let me phrase that a little bit more tweetably. Software engineers can build double entry bookkeeping every day. Okay? This thing took hundreds, if not thousands of years of banking, of bankers, accountants, before it was developed. Okay? We can build Newtonian mechanics every day. Right? So Newton had this quote, "If I have seen further, it is by standing on the shoulders of giants." Now it sounds like a humble thing to say, but he wasn't humble, and he actually said it as like a joke because one of his rivals was short, and he didn't want to give him any credit. He's like, I was standing on giants' shoulders, not this guy. So let's see what that looks like. There he is. Newton is standing on the shoulder of the jolly green giant, seeing really far. And it's true, you know. He had a lot of, you know, books and a lot of time to develop this, like ideas from other people. That's what he means. That he was given all these perspective from other people. He could synthesize it into something new. And the way I like to see it, it's not a statement of humility. It's not a statement of you know, an insult to his rival. It's actually a statement of the method. Right? He's saying, just read other people's ideas and put them together in new ways and see how they did what they did. And that, as a method, it actually makes a lot of sense. He's telling other people how to do what he did, how to become a genius. And the thing is, when you think about it, he lived in the 16th century. Like, there have been 400 or 500 years of progress built on what he did, right? So he's one of the giants, right? So if you think about it, like, so there's a giant, and then you like put Newton on his shoulders, and then he's like a giant because, you know, and then you put someone else on his shoulders, and then more people, and like, it's hard to explain. Let me just show you. It's exponential giants. Okay? The height of the giant shoulder to stand on is going up exponentially. So that's Newton down there in the 16th century, and we're way up here. Okay? Now, my teachers always told me that you should label your graphs, so hang on a sec. Bam. So the thing is, we are able to stand on way higher giants than Newton was. In addition, we have something that Newton, or people even 50 years ago, didn't have: the computer. We have computers like all around us nowadays. And these computers, it's the untapped potential of the computer. It is for modeling. They are made for taking the shoulder of a giant and seeing from that perspective. We can pick any giant we want. We can write a program that's an abstraction from what that person was saying and see how it works. And we can generate a new abstraction, at work every day. So one of the things that I put in the abstract was that these things have tremendous business value. And I was trying to express that well when I was talking about the Medicis and their rise to power. This is something that I've experienced in my career, where because I have access to the computer as the programmer, there's different roles on the teams, and I'm a programmer, and I'm building the abstraction, I actually am building business value that the people on the sort of executive team can't even see yet, right? Because I can see that, wow, this is really an elegant abstraction that captures something that the competitors are not able to do. And I think it does. To me, like this, it's totally clear that it has a lot of business value. But deeper, I think it has a lot of personal value too. I think that we're at this. We have all this untapped potential for using computers in a way to make these powerful abstractions and revolutionize all fields of study and things in our lives. So I hope that you take away from this talk a sense of optimism, a sense of personal power, and a little process that you can put in your pocket to develop these things. Takeaway: don't implement it before you develop the meaning. And then, where does the meaning come from? Your physical metaphor, your personal intuition. Done.